In the last video, I showed an example of how you can start with a recurrence relation, use a generating function to turn that into a differential equation problem, solve the differential equation, and get back to the solution for the recurrence relation. So in this video, I'm going to use the same example, but now I'm going to start at a different point. I'm going to start with the differential equation problem and show how we can turn that into a recurrence relation, and if we know the solution to that recurrence relation, we can use generating functions to get back to our differential equation solution. And as far as I can tell, this is actually a more practical way to use these whole generating functions, because oftentimes a differential equation won't have an elementary solution, and so it can be pretty useful to turn it into a recurrence relation, and then we can get a solution in terms of a power series. So I'm just going to use the same example here, which of course does have an elementary solution. And so let's say we're starting with the function, the differential equation, that's y prime is equal to y, and we want to solve that. So what we can do is we can assume that this is equal to a power series, and so I'm just going to write f0 plus the sum from 1 to infinity of fn x to the n. So all I'm doing is I'm assuming that y is equal to a power series where fn just represent the coefficients of that power series. And so we are making an assumption here. I think we're assuming that that y is an analytic function around 0, since this is a power series centered at 0. It's x minus 0 here. But that's not a very big assumption, and it's a pretty good assumption. It works for a lot of different differential equations. So you'll notice again I stuck this f0 term out front. This is just because when we differentiate, this term's going to go away anyway, and so we're just left with the remaining terms, and now this n is just going to come down, so we're going to have n fn x to the n minus 1. And at this point I can actually do a variable shift. I can replace n with n plus 1, and so that'll tell me that y prime is equal to, now I'm starting the sum at 0 going to infinity, replacing n with n plus 1 everywhere I see it, so this is going to be n plus 1 f sub n plus 1 x to the n. And so now I can apply my differential equation. Since I have y is equal to y prime, that must mean that the coefficients of this series are equal to the coefficients of this series. So I can just, instead of writing out the entire sum, I can just write an equation using the coefficients. So the coefficients of this one are fn. So I have fn is equal to, and then the coefficients of this one are n plus 1 fn plus 1. And so this is actually the same exact recurrence relation as in the last problem. It's a slightly different form. So if you want to see it in the form that it was before, you could just replace n with n minus 1, or replace n plus 1 with n. Either way you look at it. Here we're going to get f of n minus 1 is equal to n f of n. And then if you want it exactly the same way as in the last equation, you can, in the last example, you just divide by n. So you have 1 over n, fn minus 1 is equal to fn. These are all equivalent. But the point is, if you get it to here, it's often easy to solve this equation using guessing, even for more difficult differential equations. And so let's say we know the solution to this, and you can find it using guessing, using induction and stuff like that. So let's say we know it, and the solution is it's going to be a constant over n factorial, and actually this constant represents the 0th term in the sequence. And that's easy to verify by just plugging in f0 here. So what this means is, since y is just equal to a series with coefficients fn, this means that y is equal to, now I'm not going to bother writing this 0th term out front here because there's no point to anymore. I can just say that this is, well, this was going to be fn before, but now I can just replace this with what I know it is, which is a constant over n factorial. And so this is really, if you take out this constant, you can see that this is just the series for e to the x. And so this is another way to solve a differential equation.